So what we found out about the T's and the R's in the symmetry groups, algebraic symmetry structures that we were working with, is that because of the rules for simplification that we knew with T's and R's, we could, given any word spelled out with the T's and R's, we could push all the T's all the way over the left side and all the R's all the way over to the right side. And because we know how many powers of T equal the identity and how many powers of R equal the identity, we can then simplify completely down to, for example, in the symmetries of a square, only 8 different symmetries are possible. The identity, three versions of R, of the different exponents without a T in the front, and then 4 versions that have a T in the front, and however many rotations. Because as soon as we got to 2 powers of T next to each other, what happened? It canceled. As soon as we got to 4 powers of R next to one another, they canceled. They were just equal to the identity. And so what you discovered last time was that for a square, for example, so where's my square group? It's like, who was working on the square? Yeah, because you should be distributed. How many elements were there? How many different symmetries were there for a square?
8.
There were 8. And here they all are. Okay. So what we want to do today is we want to think more about how those 8 different elements interact one with another, or how to come up with a way of communicating the larger algebraic structure in as explicit a way as possible. And one way of doing that is shown up here on the screen. It's called a multiplication table, which should be a fairly familiar thing if you've ever been a second grader or third grader, I suppose. I think most of us have. What does a multiplication table do? So how do I use the information that's in this table? So multiplication tables work the way that we know multiplication tables to work, that we locate an element in a given row, a symmetry, for example, in a given row. So yeah, you locate an element on the row, a symmetry on the row, and then you locate a symmetry on a column, and then the product is what you get inside of the table on that row and on that column. So for example, if I wanted to use this table to tell me what is tr squared times tr to the 3rd power, or something like that, how would I do it? Where would I go first? Where would I find, let's say, tr squared? Yeah.
Tr squared in the row.
I would find tr squared on the row, right. And so I would look at the row that has tr squared in it, and then what?
Then you go to tr cubed in the column.
The column that has tr cubed. And what is the product according to this? Product is r. You should check that answer based on what we know about the symmetries of a square. Right? But this is a nice, really convenient, very explicit way to show us what are all of the different quote-unquote products that we can have inside of this algebraic structure. By the way, why is it important for us to decide whether we should find tr squared on this row first, or whether we should find tr squared up here in the columns first? Does it matter? Why does it matter? How do we know that it matters? Yeah.
Because the operations, we know they're not commutative.
The operations we know in this particular example are not commutative. So if we were to do it the other way, if we found tr squared in the column and tr cubed in the row, what would the product end up being? Yeah. So that means that when we use an operation table, and that's what we're going to call these, operation tables. When we use an operation table, we have to decide up front how that table is going to carry information. And the way that we decide it is that we're going to find this first element on the rows, and we're going to find the second element on the columns. That way we don't get turned around, because in general, getting those two mixed up can change our answer, because we don't always have the commutative property that multiplication of integers happens to have. So today is all about the study of these, what we call binary operations. A binary operation is nothing more than a process that takes 2 elements and produces for us a third. Right? It takes 2 objects and produces a third object for us. So here, this binary operation is the composition of symmetries inside the symmetry structure of a square, and the operation just does one symmetry after the other. Right? So that's what we mean when we say times in this particular setting. I and other people who do abstract algebra will often talk about products and times and multiplication tables, but don't be fooled. It's not always multiplication. They're not always numbers, for the same reason that we're looking for the structure, the abstract structure behind the specific cases with numbers and multiplication and all the stuff that we learn in grade school. So the goal for today is that each of your groups has been given a structure. And that structure has 4 different elements in it. So all of your structures have 4 elements. And I've specified what is the binary operation in that structure. Your job is going to be to come up with the operation table for that structure. So since your structure has 4 elements, your table is just going to be 4 by 4, 4 rows, 4 columns. Divvy up the work a little bit if you need to. One of your groups is going to be doing matrix multiplication. That group definitely probably wants to divvy up its work just because it's a little bit more laborious. The other groups, one group has symmetries of a square, one group has symmetric difference of sets, and one group has, what's the last one? Complex numbers, multiplication of complex numbers. But all your groups have a set with 4 elements and a binary operation that's been described. I'm going to give you all a big sheet of paper, and I'd like for you to make a large, with a marker, operation table that we're all going to be able to see after you're done with it, because we're going to regroup into groups and do a gallery walk around the room.